Welcome to a lesson with Dr. Powell. Let's take a minute and look at geometric series and when they converge and when they diverge. So, in general, when we have any kind of geometric series, so it might look something like 5 times, maybe it's like a half raised to the n plus 3, and maybe it's like starting at n is equal to 2 and going on forever. So no matter what our geometric series looks like, if you take the first term and like take your first term and you factor it out of your whole series, you're just left with an infinite polynomial or infinite series looks like this, like 1 plus r squared, where r is, in this case, 1/2. It's what we're multiplying by to get from term to term, plus r cubed plus r to the fourth plus dot, 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 dot forever. Um, um, quite literally, because the first term, you multiply it through to the 1, it's the first term. Multiply first term to r, because how do we get from first term to the next term is we multiply by r. Okay, so the second term will definitely be first term times r, and then the next term will be that times r again. So really, we just get this nice infinite polynomial going on. Now, if we were to stop at a point, let's just stop right here, do a partial sum where we have 5 terms up to r to the fourth. This polynomial right here is the quotient of 2 polynomials, r to the fifth minus 1, all over r minus 1. Now, where this 5 is like the number of terms you see there, and that's times the first term. Now, let's investigate. When the absolute value of r is less than 1, then when we take a limit, r to the n, the limit as n approaches infinity, we actually get 0. Now, when r is positive, we could actually graph this. It looks like exponential decay. However, when r is negative, we get, so this is if we make, n like a continuous variable. But if we make r negative, x cannot be really a continuous variable, at least real, in a real sense. So you're going to have bouncing around. It's going to look like, quite literally, if we connect the dots of what's above, it'll look like exponential decay. And then here it'll look like decay to an asymptote going up that way, and it will converge. And it converges at 0, even still, even when r is negative. For instance, like negative a half, because for even n, that's going to be like up here, and for odd n, it's going to be down here, but eventually it's going to converge to 0. So we have, when the absolute value of r is less than 1, converges to 0, or this limit right here is 0. Now, if so this is like adding up 5 terms, but if we're adding up n terms to get a formula for the nth partial sum, it'll look like first term times that. And we know when we take a limit, this guy will go to 0. So we can just ignore it. So if we're finding the infinite sum, it'll be first term times this, and we can multiply top and bottom by negative, which would just turn into first term on the top times a positive 1 divided by 1 minus r, where we multiplied r minus 1 by negative 1 to get 1 minus r, and negative 1 times negative 1 to give you 1. So it's just first over 1 minus r. And this is, we have a nice slick formula for the sum of a geometric series dependent on the fact that the absolute value of r is less than 1. Now, however, if the absolute value of r is greater than 1, then what happens to this limit? This limit will actually be infinite. It'll be infinity. And we'll definitely have divergence here. So a geometric series will actually diverge when when the absolute value of r is greater than 1. It'll converge when the absolute value of r is less than 1. Diverge, converge. Now, what about when r is equal to 1? So that would be like 1 to the n or negative 1 to the n. So when you factor out the first term, in this case, you're just adding up ones, an infinite number of ones, in fact. So that's just 1 to an infinite number of ones, which doesn't converge. Here you're bouncing back and forth between 1 minus 1 plus 1. But if you just take a look at the sequence of partial sums, so up to this point you add, then here you're at a point, then here you're one less than that point, then here you're back to that point, then you're one less than that point, then you're back to that point, and so forth forever. So really your sequence of partial sums looks like something like this. And it doesn't converge to anything. It's always bouncing like that forever and ever. So it doesn't converge. So it actually diverges, not off to infinity, but just because it doesn't narrow in on anything. When, at least in the case of -1. But 1, it definitely goes off to infinity that way. So we can just say, if the absolute value of r is greater than or equal to 1, then it diverges. If the absolute value of r is less than 1, then it converges. So this is something that we use for geometric series. Now, when we're going to be looking at series in general, actually, often we relate it to a geometric series via a ratio test or an nth root test. So that actually relates it to a geometric series behavior a little bit. Now, this geometric series test right here actually tests for absolute convergence. Notice that we're just focusing on the absolute value of r, which is kind of like focusing on the absolute value of the terms. So really, this test tests for absolute convergence only, really, here, if we kind of throw this in. So the geometric series test is an absolute convergence test. It doesn't dwell or focus on alternating, just absolutes, absolute values. Okay, so it's not conditional convergence, it's absolute convergence when we look at this geometric series test. And the tests that we use to link series to geometric series will also be absolute convergence tests. Okay, so this concludes this little introduction, or at least little thought process on geometric series and when they converge and when they diverge. Thanks for watching.